Hello everyone, I'm going to talk about that GSF-locality is not sufficient for proximity-oblivious testing, and this is joint work with Isolde Adler and Pan Peng. We want to solve a decision problem. So for a given input, we want to decide whether the input is in the property P, in this orange area in the picture, or is not in the property P, in the blue area. And now let's consider the case that the input is so large that we can't even read it once. And in this setting we can consider the framework of property testing, which was first introduced by Rubinfeld in Sudan and then extended to graphs by Goldreich, Goldwasser and Ron. And in property testing we consider solving a relaxation of the decision problem. So for a given input, we have to decide whether the input has the property or is epsilon far from the property. And we have to decide this only with high probability correctly. And if the input is in this epsilon ring around the property, then we actually don't care how we decide. And the property tester is given query access to an input, and this allows us to consider sublinear running time. And in this setting, the distance and the query access are model dependent. And in this talk, we only care about constant query complexity. So we say that a property is testable if for every n and every epsilon, there is an epsilon for Pn. This is the property of inputs of size n, which takes a constant number of queries. And here the constant number of queries, this can depend on epsilon, but it cannot depend on n. In this work, we consider a special type of tester, so-called proximity-oblivious tester. This concept was first introduced by Goldreich and Ron. And POTs are restricted types of testers in which a basic test is performed some number of times. And the query complexity of the basic test cannot depend on epsilon, but the number of repeats can depend on epsilon. And again, we say that a property is PO testable if for every n there exists a POT for Pn with a constant number of queries. There are some results which kind of lead into the direction of a characterization in the bounded degree model. There is, for example, a characterization of PO testable properties by Goldreich and Ron. We will talk about this a lot more in this talk. Then there's a characterization of one-sided arrow testable monotone properties and hereditary properties by Ito, Corey and Newman. Note here the testers are less restricted, so the only restriction is that they're one-sided, but then the types of properties are restricted. And then in this paper it's also shown that every one-sided arrow testable property is close to being GSF local. This condition of being GSF local I will introduce in a minute, but this kind of is one direction of a characterization. But we don't know about the other direction. As I mentioned before, in this talk we consider the bounded degree model. And in the bounded degree model, the input graph always comes from the class CD of graphs of bounded degree D. And the property is just any subset of CD which is closed under isomorphism. Then we define the distance as followed. For any graph G, that the graph is epsilon far from the property P if it takes more than epsilon times d times number of vertices, edge modifications to make the graph G have the property P. And then we allow neighbor queries in this model. This means that for a given vertex V and some number I in 1, 2, D, we are allowed to query the ith neighbor of V. And we get this neighbor or a special symbol if the vertex has fewer neighbors. we need a generalized version of subgraph freeness, and for this let us consider a graph F of bounded degree for which some vertices are marked as full. Then we say that F is a generalized subgraph of G if F is a subgraph of G with the extra condition that if a vertex is marked as full, then the neighbors in G of that vertex is the same as the set of neighbors of that vertex in the subgraph. Let us look at an example. So if we consider the marked graph F here on the left, where this isolated vertex is marked as full, then we can see that F is a generalized subgraph of G1 and G2, but not of G3, because however we embed F as a subgraph into G3, the isolated vertex will have a neighbor in G3, which is not a neighbor in the generalized subgraph, in this marked graph F. Sorry. And this notion appears very naturally in property testing in the bounded degree model. Because when we query a graph, we basically see a subgraph of the graph. But for every vertex where we query all the neighbors, so we make the queries V1, V2 up to Vd, so we also get the additional information that this vertex doesn't have any other neighbors, which is exactly expressed by that vertex being full. So when we explore a graph by neighbor queries, we actually see a generalized subgraph of the graph. And then we define a property P to be GSF-local if there is a sequence of marked graphs of bounded size, such that if G is in the property and G has n vertices, then it cannot contain any graph in Fn as a generalized subgraph. We say that a GSF-local property is non-propagating for a sequence F if P is F-free, and if for every graph such that there is a graph of the same number of vertices in the property, there is a set of vertices which intersects all copies of graphs in Fn, such that the graph can be modified into having the property by a number of modifications in the order of the size of B. This basically means that if we can witness the forbidden subgraphs in only a few vertices, then we have to be able to modify out all the forbidden generalized subgraphs with a small number of modifications. We say that a property is non-propagating if it's non-propagating for some sequence. So note here that it's not for all sequences, it's just for some sequence. Let us look at an example. So this example came up in personal communication with Shapira, but it's also very similarly in the Goldreich and Ron paper. So we consider the property P of bounded degree 1 graphs, which is defined by the following sequence of forbidden subgraphs. So we again we look at the subgraph F we've seen before, and we forbid F for every number of vertices. And what does this look like? Well, this basically says that a graph can't at the same time have isolated vertices and edges. So every graph in this property is either a collection of isolated vertices or a collection of edges. So now if we look at the graph which consists of an isolated vertex and k edges, then we can pick the set B to just contain this isolated vertex, right? Because this intersects every copy of this forbidden subgraph F. But to modify this graph into having the property, we need to make k times size of b modifications. And in general, this is not in O of the order of b. So for this sequence, this property is propagating. But we can pick the sequence slightly differently. So we can choose the second marked graph f tilde, and then for an even number of vertices we forbid f, and for an odd number of vertices we forbid f tilde. This basically comes from that on an odd number of vertices I can't have a graph just consisting of edges. We always have to have an isolated vertex somewhere, and hence all odd graphs in the property are just the ones on just isolated vertices. And then if I look at a graph as before with some uneven number of isolated vertices and some number of edges, then of course to intersect all forbidden subgraphs I have to intersect every edge, and hence the set B here is large, and the number of modifications is kind of in the order of the size of B. And hence this property is non-propagating for the second sequence, and because there is a sequence for which it's non-propagating, it's non-propagating in general. And now we can actually state the characterization Goldreich and Ron gave in their paper of Potestable properties. And this states that a property P is Potestable in the bounded degree model if and only if P is GSF local and non-propagating. And in the context of this result, Goldreich and Ron formulated an open question, and this is it the case that every GSF local property is non-propagating? And in our paper, we give a negative answer to this question. We prove that there exists a GSF local property that is not testable in the bounded degree model. And since non-testability implies non-PO-testability, combining this with the characterization of Goldreich and Ron, this implies that not all GSF local properties are non-propagating. We show existence of such a GSF local property which is not testable by using a recent result of ours which shows that there's a first order logic property p zigzag that is not testable in the bounded degree model. And graphs in this property have roughly the following structure. So there are a big d-ary tree where on every level there's an expander sitting. So the vertices on each level form an expander, and these expanders come from a recursively defined expander construction which uses the zigzag product. And then we can actually show that these graphs are actually expanders themselves, and this implies non-testability, because by a recent result of Fichtenberger, Peng and Sola, every testable property must contain a hyperfinite subproperty, and a property containing exclusively expanders can't have a hyperfinite subproperty. So the plan is to show that this property P zigzag, which is Fdefinable, is also GSF local. And in order to prove this, the first question we could ask is what the relationship between Fdefinability and GSF locality is. And sadly, we can observe that they're kind of different concepts. So that neither of them is contained in the other. So there are things we can define in FO that are not GSF local. For example, we can say that there has to exist a vertex with a certain fixed neighborhood. Can, for example, define the property of all graphs which are non-empty in FO, but we can't define this in with generalized forbidden subgraphs. And then there are also things we can define with forbidden generalized subgraphs, but not in FO, for example, parity. And this is because in the definition of GSF-locality, we can use this sequence of forbidden graphs. And this allows us to, for example, define the set of graphs with an even number of vertices. And this is not FO definable. So I will now introduce a way of thinking about first-order logic, which I think is particularly useful in the context of property testing on bounded degree graphs. So if we fix a degree bound D and a radius R, then we can list all R neighborhood types of bounded degree D, and we just call them tau 1 up to tau k. And then the frequency vector of a graph G is the vector whose ith entry is the number of vertices whose R neighborhood type is tau I. And then we can define the concept of neighborhood profiles. And a neighborhood profile is just a function which maps 1 up to k into a set of intervals. And these intervals are either closed intervals with natural bounds or infinite intervals. And then a neighborhood profile defines a property, and this property is basically all the graphs of bounded degree which obey this neighborhood profile. And by obeying a neighborhood profile, we mean that for every I, the ith entry of the frequency vector has to fall into the interval rho I. And then by Hanf's theorem for first order logic, it's very straightforward to see that a property P on bounded degree graphs, here bounded degree is important, is FO definable if and only if P is a finite union of properties which are defined by neighborhood profiles. Let us have a look at a quick example. So let phi be the following formula. So this formula says for every 2 vertices there's no edge, or for every vertex there are 2 distinct neighbors of the vertex. And then the graph has to be non-empty. So this property is the property of all non-empty graphs which are either a union of isolated vertices or every vertex has degree at least 2. And then for bounded degree 2, we can list all 1 types, so all radius 1 neighborhoods. And then we can easily see that this property, which is defined by this first order logic formula, is also defined as the union of these 3 neighborhood profiles, while the first one captures that the property is a non-empty union of isolated vertices. And then the second and third, we have to consider 2 different options, because if every vertex in the graph has degree at least 2, then we basically allow neighborhood type tau 3 or tau 4, and we know that one of these has to appear at least once, but we don't know which one, and that's why we get 2 more profiles. But yeah. As I said before, we can't express that a certain vertex appears in a graph with generalized forbidden subgraphs. So it is kind of a reasonable assumption that if we set all the lower bounds in a neighborhood profile to 0, then we might have a chance to express this with generalized forbidden subgraphs. And for this purpose, we introduce 0 profiles. These are just neighborhood profiles where all the lower bounds in the intervals are 0. And then indeed we can show that every finite union of properties defined by 0 profiles are GSF local. And for this we can first think about how we can express forbidding a certain neighborhood by generalized forbidden subgraphs. So if we're given an R neighborhood tau I, then we can consider all R plus 1 extensions of tau I which have bounded degree D. So these are all the graphs of radius R plus 1 who contain tau I as the restrictions as the restriction to radius R. And then we, in all of these extensions, we mark all vertices of radius at most R as full. And then it's very clear to see that if we forbid all these extensions, then we can't contain tau I as a neighborhood. And it's also clear that if we contain tau I as a neighborhood, then one of these extensions has to appear. So it is equivalent to forbid tau I as a neighborhood and the generalized subgraphs that come from these extensions. And then the next step is, because in a neighborhood profile we are given that the upper bound of appearances of a certain neighborhood type is, for example, L minus 1. And this means that we have to forbid L appearances of neighborhood tau I. And this we can do by considering forbidding all generalized subgraphs, which are kind of not necessarily disjoint unions of these extensions we had in the first step, for which the centers don't coincide. Because if the centers coincide, then obviously the neighborhood tau I doesn't appear twice, it appears only once. So we have to make sure of that, and we have to pick the markings in a suitable way. But yeah. And then we can basically express the property defined by a zero profile, because we just take all these for every I in 1 up to k. And then we just have to see what happens with unions. And this is very straightforward as well. So if we have two sets of marked graphs, F1 and F2, and Pi is the set of graphs which is Fi free, then we can define the union as the set of marked graphs F, which basically contains all not necessarily disjoint unions of a graph out of the one set and a graph out of the second set. So let's evaluate what we proved so far. So we have the set of GSF local properties, and we know that from the Goldreich and Ron characterization, we know that the set of all properties which have a POT is kind of a subset of these. And then we know that first order logic might intersect the set of GSF local properties, and in fact we know that in the set of in the intersection of GSF local properties and first order definable properties, we have the set of properties defined by zero profiles. This is what we just showed. And then it's also quite easy to find examples separating these areas. So I already told you about P1 and P3 basically. P2 is a bit trickier but also reasonably straightforward. You can have a look in our paper if you're interested, but there's a property which is definable in which is definable in FO and has a POT, but is not definable by zero profiles. Then of course the set of all graphs has zero profiles, so is and a POT, so is right in the intersection there. And now we basically know for the property P zigzag, we know that it's FO definable, and hence we want to show that it's GSF local by showing that it's definable by zero profiles. From that it's definable by first order logic, we just know that it's in general definable by neighborhood profiles. So all we need to argue is that this property is defined by a union of zero profiles. And for this, let us quickly recall that the property was kind of consisting of graphs which were full trees, where on every level there's an expander. And now the first idea would be we could compute the Hanf normal form, which is kind of the normal form that comes from Hanf's theorem. And then using this normal form, we can actually compute a representation by neighborhood profiles. And then we might be lucky and it's all zero profiles, or we could maybe try and simplify. But this is very impractical because the formula which defines this property is really, really complicated and very long. And this, the Hanf normal form and the representation by neighborhood profiles will be very complex and very, very large. So instead, we just guess a set of zero profiles. And for this, we partition the property P zigzag into parts S1 up to SL, such that the root element, you recall the graphs are all trees and hence they have one root. So the root element of every graph in Si has the same R type for some radius R we fixed. And then for each of these parts, we can define a zero profile, which hopefully will express this part. And this we do in a straightforward way. So for the type of the root element, we say that it's allowed to appear between 0 and 1 times. And then all other types that appear as a neighborhood in a graph in Si, we allow to appear as many times as they want. And all types that don't appear, we forbid. And in fact, this works, so we can show that the property P zigzag is the union of the properties defined by these neighborhood profiles. And the one direction that P zigzag is included in the union of the properties defined by the row I is really straightforward, because every graph in P zigzag is in one of the parts, and then it's very easy to see that a graph in one of the parts obeys this profile row I. And the other direction is a lot more complicated. For this, we can imagine that so we are given a graph that obeys one of these profiles, and then we can basically dissect the formula into conjunctions, and each of the conjunctions has to hold. So we prove it for each of the conjunctions separately, and then we assume that one part of this big conjunction does not hold for our graph, and then we can observe this already in the neighborhood, and this has to be carefully argued. And if we can already observe this in the neighborhood, then we can argue, because this neighborhood appeared in a graph having the structure, then we can argue that there's a contradiction. And for this, indeed, the one of the key observations is that we can relax saying there's exactly one root to there's at most one root. This is important for being definable by zero profiles, obviously, because... And of course, I'm omitting a lot of technical details here. For example, the property P zigzag is actually not a property of undirected graphs. It's a property of edge-colored directed graphs. So in the paper, we have to reduce this to the case of undirected graphs in the end, and construct a neighborhood profile for that as well. Okay, but this is the proof idea. So we showed that not all GSF local properties are testable in the bounded degree model, and this has some consequences. And first of all, the non-propagating condition in the Goldreich and Ron characterization of Potestable properties is necessary, and this answers their open question. And then second of all, I showed you right at the beginning that e to Corey and Newman proved kind of the one side of a characterization for one-sided error testability, which was by generalized forbidden subgraphs. And our result basically implies that this cannot be made into a characterization result because the other direction does not hold. And this was also asked as a question in their paper. So in general, what I think is the most important open question to make progress towards a characterization of testability in the bounded degree model is to understand this propagation. So in this context, it would be nice to find other examples of GSF local properties that propagate, because we've seen one very specific example, and it would be very good to see different examples. And then, of course, it would be good to aim for a characterization of when GSF local properties propagate. Thank you for your attention.